So, yes, on previous class we have discussed separable and non-separable extensions. So maybe now I shall just have turn to so maybe let me continue with non-separable extensions. So today we shall discuss the following theorem. So the aim is to recall the notions that are known, that are needed to prove the following theorem, that if you have extensions of the field and so let me write it down. So aim is to prove the following, so that if you have EF extensions of the fields, and here we have A is the ring such that fraction field, without zero divisors of course, so the fraction field is equal to F, so and so we consider B is the integral closure, integer closure of A in B in E. So then we will find out that B is position. That we shall see that then B is finitely generated a module Moreover, you can find the integers, so we can find the basis. So we can find the basis. Find the basis. Omega 1, omega n, where in E, where n is degree of the extension.
So it's finite extension.
Yeah. So finite extensions. We'll put it from the beginning. Otherwise there is no reason to have it. I mean the problem even yes. So also. So also we have to need additional condition that A is algebraically closed in F. So
integrally.
Integrally closed in F. Otherwise it is also not true. So that means in its fraction field, and so we can find the basis such that we can bound B between moreover omega I belong to B, any I, and we can, and there exists some D that belongs to A, so such that we can bound B by the following. So B contains, as we have seen, the basis is contained in B, so that we can consider A omega I the direct sum, and it is contained in B, and B is contained in 1 over D, this direct sum. So in a sense, B behaves like a to the power n, but I mean, it is close to that, yeah, but the problem is that for arbitrary ring, you cannot say that, for example, a submodule of free module is free. Yeah? So, for example, if you take a polynomial ring, you take any ideal, if you have an ideal with many generators in the polynomial ring, then it cannot be a free module because on one hand its dimension should be should be equal to 1, and it should be generated by one element, which is not true here. So yeah, but for number theory we can bound this thing by this between these two objects, and that will be just an important property that we shall use when we shall study number theoretical things. So okay, so let me now continue with separable and inseparable extensions. So the last remark I wanted to just tell, it is just for your, I mean, for your educational purposes, we shall not consider inseparable extensions, but we can write down characterization of inseparable extensions. Yeah, I mean, when we consider a number theoretical problems, of course, that are extensions of Q, so there is no reason of speaking about inseparable extensions. But however, there are situations where this most of the theorems, technical theorems that we're discussing, are true in a larger setting. For example, when the ring is Dedekind, meaning that it is one-dimensional, and and in particular it means that it is one-dimensional. And so as an example of such ring, we can think of the ring of functions on the curve. So we have C is some curve, and we can consider a affine chart. So we can think of this as a affine curve, meaning that it is sitting in a affine space. And we can think of the maps between the curves, and what formulas that are related with number theory is to give several just interpretations how the preimages. So suppose you have maps between two curves, and the set of the theorem says that how these preimages of the point on one curve behave on the other curve, and that's why this this setting can be done when a curve is defined over, for example, algebraically non-closed field, and in this setting, non-separable extensions, of course, can arise. So that's why we really take some time to speak about that. And yeah, so the following conditions are equivalent. So first of all, that separable degree is equal to 1, yeah, so that the second is that there exists so any element extension E over F. Yeah? So any element of E is inseparable. Over F, meaning that it is a root of, so its minimal polynomial has multiple roots. Or we have described how this polynomial look like. Yeah, so then the claim is that irreducible polynomial of alpha f is equal to, so actually the inseparable meaning, so if you know that any element that is not in the field is inseparable, this really allows you to make a reduction of the polynomial that says that the polynomial is actually of the form x to the power pn minus a. Yes, so where a belongs to f, and for any alpha belongs to E, and alpha not in F. So, and the last claim is that you can add, so you can obtain E by taking elements, adding elements which are just the if power, some roots of the polynomials where that are just of the form of this form, precisely of this form. So alpha I are roots of x p and I minus ai equal to 0.
Yeah, and when we say such statements, we always assume that this finite extension.
Yeah.
So we just always assume
yeah.
Okay.
So, yeah, but sometimes it is done purely, at some steps you can simply do not assume that the extension is finite, but you have to assume that it is algebraic. Yeah, so that any element that you extend is a root of algebraic polynomial. Yeah, so for example, how we can obtain from 2, how we can obtain 3. Yeah, so that if you have just, we have noticed that if alpha is inseparable, yeah? So let me write down 2 implies 3. Yeah? So then alpha is a root of polynomial just where you have p p should be contained in, so all powers should be divisible by p, yeah, of this polynomial. If it is non-separable, so in order to guarantee that derivative is equal to 0. Yeah? But then, so this is a polynomial h of x equal to 0. But then you can write down this polynomial as f x to the power p equal to 0, as we have done it, yes, so by where f is just x to the power n and where you do the reduction, so you just divide by p all the powers of x. Yeah. So if notice that here, if you have element which is a root of h, yes, or alpha is a root of h, then alpha p is of course also element of e. So if it happens that you see that you reduce the degree of the polynomial, still you can ask if it is separable or not. But if you know that all elements are inseparable, then this polynomial is still inseparable. So if true hold, then alpha p is inseparable. So f is inseparable. Then we can proceed. Yeah, and so maybe other options should be put as an exercise. Yeah, so. Yeah. So, yeah, for example, and from the last part, from 4, you can derive 1, meaning that you should have only one separable from 4. We can derive 1 by the following. So notice that this means that there is precisely one, one way. Meaning that separable degree is 1, meaning that there is one way there is a unique way to extend inclusion of f inside f bar. But this is also evident because for roots, yes, so we recall that taking, this solution of the equation is unique, yeah, in characteristic P. And that's why we map, yeah, so this means that we map each alpha, we map each alpha I in unique solution of equation x p n I minus a I in f bar. So, for example, that means that just that already, if you know that f sits in a bar, yes, so all other elements, so all other roots are mapped uniquely. And for example, if you have yeah, so maybe it is yeah. So other things should be done as an exercise. Yeah, so now I wish to discuss norm and trace, and surprisingly, so that this so norm and trace can be defined and by different formulas and by from different points of view. But this kind of descriptions via inclusions formulas that can be described via this inclusions of E into algebraic reclosed fields are quite important. So that's why we shall also use them. So norm and trace. Yeah, so notice that So even so here we can think of so A is finite dimensional vector space over K. And assume that A is algebra, is K algebra. Yeah, so A is K algebra, possibly non-commutative. Then we can do the following. So then we can consider operators. So all shifts that the left multiplication and right multiplication. So L of AX is just AX and right multiplication. Yeah, so then we can pick a basis over, so pick a basis over A over K.
Okay.
And this will make this operators just between the vector spaces. So that means so you can take the usual trace as the trace of linear operator. So this becomes linear operator. And on this finite dimensional vector space, and you can pick up so define trace and determine and norm. We are taking usual trace so linear operator given by matrices, matrix AIG. So we are taking usual trace or determinant. Yeah, so of course trace is just the sum of the organal elements. Of course there are conceptual ways to do it, but they are surprisingly that they are more complicated than just checking this kind, writing down this formula. And so for determinant, yes, so again this is usual norm is just determinant of norm of A is the determinant of this matrix. Yes, so we use a left shift for just in order to fix the notation. And yeah, for example, Yeah, so where you can use this as an example of finitely generated algebra, for example, non-trivial one is k of x modulo x cubed. And so where you can also write down these formulas not only in the fields. And of course, you have the properties that you have for the trace, yes, so that norm. So since you have L of A, B is equal to L of A times L of B, yes, so and determinant is multiplicative, so determinant of AB is equal to determinant of A times determinant of B. Yeah, so you see that norm AB is multiplicative thing. And trace is additive. Yeah? So trace of A plus B is equal to trace of A plus trace of B. So trace is a linear function on the algebra. Yeah? So in particular, you can think of field extensions. So let me write down in several. Yeah, and when you're thinking about the trace for field extensions, you may write. So I mean, if you fix field extension E over F. So extension then you may write down for the trace, so you can introduce notation where you are writing down. So for the trace, you are writing down you are recalling extension in the notation for the trace. So the reason for this is the formula that we shall need is how trace is changed under extensions. Yeah, so proposition trace of T over F. Yeah, so suppose you have 3 extensions. Yeah, actually 2 extensions. So E over K and K over F. Yeah, then you have the following. So then you have the following map for the trace. So trace of E over F can be obtained as first you take trace E over K, and then you compose it with the trace of K over F. And yeah, so this this tells you that the function behaves well under the field extension. And this yeah, so for example, you can yeah, so we shall discuss this proposition just slightly later. And now I want to try to calculate several examples where that are crucial for from the calculational purposes. Yes, so suppose you have elementary extension. so meaning by one element. So your alpha is the root of some polynomial, a reducible polynomial. And so of course it is. So here there are actually two ways one can choose the basis. Yeah, so notice, so what is important about the bases here. So as a remark for the calculation of the trace, yeah, so that when you calculate the trace, it is not important over which field you calculate the trace. Yeah, so as meaning that, so notice that this is linear operator. Already it is given by this matrix, yeah. But yeah, so so here maybe I should write down as the remark. So when you want to calculate the trace, so if you have an arbitrary linear operator, so that looks like this, with so given by matrix. This matrix. So also you can take tensor product, for example, with any field and any field that extends K. For example, algebraically closed field. So suppose E extend, so big K extend K. So big K extend K. And this you can think of the formula. A over K, the map from Kn to Kn, given by the same matrix, so given by Aig. Yeah, and when you give this thing by the matrix, yeah, so when you give this thing by the matrix, you know that yeah, so you can think of this, of course, as formula multiplying. So taking the tensor product, yeah, so you take Kn, the tensor it by K, and yeah, so simply consider the operator induced on the tensor product. Yeah? But it is just, but it is, if you do not want to pick up basis, you may think it like this operator. If you already have picked a basis, it is even easier to say that you are giving it by the same matrix. So, but if you calculate the trace, so the trace of A is of course is equal to the trace of AK, yeah, because they are given by the same matrix. But in order to calculate the trace AK, you can use different bases. But to calculate AK, trace of AK, we can use basis. Defined over K, big K. So meaning that we have done linear transformation over larger field, and for example, this matrix a priori over K is not diagonalized. Yes, so we shall see now the example of the matrix. But if you are thinking about algebraic extension, then you can diagonalize this. For example, if you have a matrix of finite order, yes, so that or a priori diagonalizable matrix, then you can diagonalize it, and somehow it is easier to calculate trace. So that now we shall discuss this. Yeah, so this, yeah, and of course, yeah, I didn't say it explicitly, but I hope everybody knows that that trace, however it is written in the basis, the trace itself, the value doesn't depend on the basis. Yeah, so that, yeah, so for example, due to the following formula that trace AB is equal to trace BA, that says that trace of A, B, A minus 1, the change of basis result that it is traceable. So this tells you that trace is independent, and you may calculate in any preferred basis you like. So if you consider this kind of polynomial, that is a minimal polynomial for A, of course, that we can write simply an operator that multiplication by alpha. Yeah, so it is given as follows. So the matrix, of course, is not, will be not in the diagonal form. So you'll have alpha I will be mapped to alpha I plus 1. Yeah, and alpha n minus 1 is mapped to minus alpha n minus 1, alpha n minus 1, etc., plus alpha 0. Yeah? So, yeah, so the matrix, yeah, if you want to calculate the full trace, yes, yeah, so let me write down the matrix. So let me write down the basis. So alpha n minus 1. So I'm just drawing the matrix. Yeah, so and I'm making it like, so I'm writing down the image. So how it should be again look in the basis. In the coordinates from 1 to alpha n. So here I should put what? So on the 0. So here 1. Yeah, so here I put all zeros, here I put all zeros. So on the diagonal, except the last term I'm putting zeros. So once downstairs, down the diagonal. And however, there is so for alpha n, there is different formula, and I'm writing down only minus a0, etc. And here you are writing
minus a n minus
n minus 1.
Mm-hmm.
So you see that the trace by this formula, yeah, so that trace of A is equal to what?
Minus a.
Yeah, so all elements are diagonal except this one. Yes, so minus a n minus 1. Yeah, and if you want to write down the trace, of course, if the element is already in the field, then you write down it is identity, it is just one-dimensional vector space, and you multiply by the element from it, and the trace is just so the operator is scale, and you just write down this element for the trace. And also, you can calculate, but by the way, you can also calculate the determinant. So the norm, what is norm?
Minus A0?
Almost, but
It should be.
so there should be a sign.
Yeah.
So the sign is just minus, so I think like this, with, so I mean with n, so normal, it should be like this, because only a non-zero block that can be taken from the non-zero elements are just on the lower diagonal, and then when you have taken all elements from the lower diagonal, you can take minus A0, that gives you, and you have to put the corresponding sign. So the thing is that, so when you want to calculate the same thing for the extension that is larger than elementary extension. So of course the situation usually is the follows. So you have a big extension E. And you have extension F, and you want to take a norm of the element. And you will take this element, if it is not in F, it is a root of a reducible polynomial, of minimal polynomial, but it can happen that when you add this element, you do not obtain the whole field E. So that's why, due to our formula, so of course it is tempting to write down that the trace of this element is just this number, but you are thinking of it as from the viewpoint of the large extension E. So that's why we are writing down that trace of E over F of alpha is obtained as a trace of E over F alpha and trace of sorry, you first have to review that. So trace of here you are doing the trace from E to F alpha, and here you are doing the trace from F alpha to F. And if you apply it to alpha, this trace, if you take the trace of the operator that already defined over the field, so if E is obtained as, let us notice that if you take E over F, so E is just F to the power n. So if you take element of F, so A belongs to F, then on the basis, so EI will be mapped to EI. So that is another example. So the left shift maps the basis diagonally, just multiplying it by the element from the field. And this implies that the matrix will look like this of the element. And so the trace of this matrix is just n times A. So when you calculate trace of extension, then you just have to write down, so here you take alpha already from the field you consider, so you have to consider E over, so to multiply it by the degree of the extension as, and then it's just degree of, here it was degree of the extension of E over F. So the formula looks like this, yeah, so minus a n minus 1 times this extensions via this formula of composition of space. So, yeah, and this, yeah, so let me discuss maybe the proof of this formula, because so actually it is funny moment because when I was looking at the literature, so I didn't see explicit proof of this formula. So the problem, I mean, it was either in the exercises or it is, but the most strange thing that in the book where it was proved by a completely different formula. And it's even more strange because the formula, it is next formula that we are going to discuss, how to write down trees in terms of embeddings. So that in terms of the values of embeddings. And this was somehow embarrassing, but the proof of this formula is more or less it is direct analysis, and I want to say what is the reason, so how it should be okay. Yeah. So yeah. So the thing is, the proof is actually based on a very simple observation that about the block matrices. But let me just say it. So suppose you have this kind of extension. Yeah. So I think I have confused.
Yeah, it should be f in the k in the e.
Yeah.
Okay.
Да, да.
Yeah, f in the k.
Да, да. Ну, раз уж. Yeah, so suppose you have an element. So here we have taken the element, and then you just consider the following. So we are considering the basis. Yeah, so let me take the basis E1 En is a basis of E, but with coefficients in K. Yeah? So the basis over K. And then you are just looking at the matrix that maps basis K1, Kn via it maps it to the vectors A, K1, etc., A, Kn. Yeah, so we are writing down it A, K1.
What is k1, kn?
Oh, sorry, E1n.
Oh.
Ну, то есть сама матрица левого сдвига, она отправляет эти вектора просто два соответствующие умноженные на все это дело. И so we are looking at this matrix, yeah, and now we are writing down this in terms of so we are writing down K1 in the basis corresponding to K1, Kn, etc. Yeah, so that Kn is written in terms of E1. Sorry. But yeah, so we are writing these vectors, and you get so here you get the matrix of linear operators. Yeah. And here you are writing down linear operator. Of course, you are then writing down the matrix. So here, phi 1, 1, phi 2, 2, etc. Phi ij, and phi, yeah, so phi ij. Yeah, so you may think of this from the viewpoint of the operator. It looks like this. So it is phi j is the element. Yes, when we are writing down this matrix, so we are writing it down as a matrix over. It is a basis E over K. Yes, so the matrix with coefficients in K. Yeah? But you may view this, yes, so as the matrix. So on one, so from the viewpoint of one-dimensional basis, yes, so it maps EI, for example. So this Pij, the elementary matrix, maps I, for example, to Kij. Ej. Yeah? So this means that when you look at this from the viewpoint of K, one-dimensional space over K, yeah, so this is a map between K and K. And this is just multiplication by Kij. And so this is operator is multiplication by Kij. So you may think of this multiplication of Kij can be viewed as the operator. So if K is equal to f to the power m, so multiplication by Kij can be viewed as operator on from Fm to Fm. Yeah? So you may think of this matrix as the matrix written as block matrix, where Pij are submatrices. Yeah? So and these submatrices are of this form. And on the corresponding matrices, you are just thinking about matrices. It is given by the corresponding multiplication by the element from Kij. So this means that you are just writing down now the trace of E over F of A. Yeah? It is equal to the sum of diagonal entries. Yeah? So diagonal entries over F, and this is the sum of matrices. Precisely, if you think of blockwise matrices, yes, so you have blockwise matrices here, F11, F22, etc., Fnn, and here you have Fij. But when you calculate the trace, you need only diagonal matrices, yeah? And so the sum of diagonal elements over F is just the sum of I, the traces of Fii. Yeah? And now the multiplication by AII are precisely the elements of key. Yeah? It is just the multiplication by AII on when you think it as the element of K, it is it is the map from K into K. And you consider it as the operator over F. So you see that trace of AII as the operator over F it is equal to trace of E over K over F. Yeah. Of the element of precisely AII written in the matrix. Yeah, so you see that when you are sorry, here I wanted to write down that so already this AII tilde the operators of so first we have written matrix in terms of as if it is it was Kij. Yes, sorry. So here I should write down Kij. So I wanted to say that. So this is Kii. Yeah? Yeah, so here I even I want to say that trace of Fii, the matrix that is standing as the matrix here. Yeah, so I mean, if you are thinking of multiplication by Kii over the basis, and here say that Kii. And here it is Fii matrix, yeah, over F. And you simply know that the trace is just this trace. And so here you are using that trace of just K over F of the sum of kii. It is written as trace over f of the operators, sum of the operators of phi I. It is equal to the trace over f of the sum of all operators of phi ij. Yeah, so meaning that this is trace of the sum of the operators, and this is trace of the whole matrix. Yes, so this meaning that it is trace of, so meaning this one is a trace of matrix formed by Fij. Yeah, so just because, so here, just because taking the trace of blockwise matrices, taking the trace of each elements on the diagonal, and it is just trace of A over F, and this is just trace of E over F of E. So that's that proves the formula. And also, yeah, so now I want to discuss the very important thing that we need to use, and we need to know that suppose the Gauss extension is separable. So this is characterization of separable extensions in terms of the trace. So the extension E of F is separable if and only if trace of E over F is non-zero function. Yeah, so this yeah, so of course one can think that so there are slight problems in order to prove it, yeah, because so for example, if you are a character, so I want to show you how to prove it in any characteristics, because it is from my point of view it is a rather non-trivial statement, and if you but in zero characteristic it is not so complicated if you know, for example, theorem on primitive element. Let us recall it anyway. That will be important for us for one of the reduction of primitive element. Yeah, so if you have E over F is separable, then so there exists an element alpha that belongs to E, so such that E is just generated by this element over F. Yeah? So this is the root of one element, and then you simply can do the following, that you can so in characteristic 0 you are just so characteristic 0 case it gives you that alpha n plus alpha n minus 1, alpha n minus 1, etc., plus alpha 0 And if you are considering such element, notice that you can, so if you are, so of course trace is just this element alpha n minus 1, yeah? So as we have noticed, but you can make always a shift, and the trace of, so you know that actually, so it is the proof of the, by the formula, but anyway, I mean, the trace is non-zero is almost tautology from this point of view, because the trace of any element, trace of unit, yeah, it is just so of E over K, of E over F, it's just E over F. It is non-zero now, in characteristic 0. And morally, so if so what I wanted to say that if you are making a change alpha to alpha plus 1, yes, so if this element is 0, yes, so it is changed anyway, alpha n minus 1 is changed to alpha n minus 1 plus, yeah, so I just you have to substitute in the corresponding polynomial, so minus what n times so binomial coefficient times this one unit, yeah, so that binomial coefficient is just n times 1, yeah. So the trace is changed, trace of the element is changed by n, yeah, so of course you're writing down minus, and the trace is just changed by the degree of the extension, as we know that I mean from the fact that this function is linear. But so morally, I mean, if you are given that formula that is related with coefficient of polynomial, or so in just knowing that the trace is just usual trace of the operator, you see that in characteristic 0, this is quite simple observation, that trace is non-zero. But in characteristic P, the problem is in characteristic P that already if you have non-separable extension, then we know that non-separable, as we have noticed, that non-separable degree is just multiple of, is a power of P. And this gives you that this number is always divisible by P when you have a non-separable extension. So, so remark. If you have E over F is non-separable. Yeah, so let me prove that the function is 0, yeah? So then trace is 0. And of course it is very easy, so you should check it for you should do it like this. I mean, it is non-separable extensions. Non-separable extension. So this means that you can either so when you are calculating degree, either the just so if you are calculating trace of alpha, yeah. So what happens? So either alpha is already non-separable, so alpha can be non-separable, Yeah, so here I want to say the following, that actually we can factor we can factor the elements in just yeah. So there are yeah. So what we have done, if you have alpha is non-separable element,
so when we talk about alpha E over F is non-separable, we're still talking in characteristic zero.
no, I mean, of course,
Yeah.
I mean,
Okay.
so I want to prove the theorem that if it is non-separable, then the trace is zero. So here it can be done as follows. So considering elementary non-separable extension, yeah? So alpha is elementary non-separable. And if alpha is non-separable, then it is a root. So notice that again we have considered a minimal polynomial. Yeah, so f of alpha is a minimal polynomial. But we can we can reduce it to h, so the polynomial to other one of lower degree. So h of alpha. H such that f is just h of x to the power p. Yeah? And you can think of so you can think of extension here. So you can take f, and you can take pth power. Yeah? So so this means that alpha p is a non-trivial element that still do not belong to f. Yeah? So that do not belong to f. So this means that you can take so if the extension is non-separable, then it always contains so there is intermediate extension which is a pth power, at least a pth power of your initial field. Yeah? And over this this extension is purely non-separable. All elements look like taking pth power of the element. Yeah, and notice that you can calculate the trace of elementary extension of alpha, where you add e alpha over e, and the alpha to the n minus ai. So sorry, alpha to p. So I wanted to say that this trace of this element calculated via elementary extension is zero for alpha of the form alpha p minus e is equal to 0, where alpha belongs to, yeah, so maybe I shall write k here. Yeah? P. Yeah? And already you see that, so this means that in particular the trace of any alpha calculated here, so trace of E over F of alpha is calculated via the trace of first from E to EP, and then from EP to F. And this thing is already equal to 0. Yeah, so that you see that this trace is equal to 0. So the reason of that the non-separable extension factors through this operation, there is somehow the canonical way to factor out maximal non-separable intermediate extension. It is done via taking all powers of B. Yeah? So, if you have non-separable extension, then it factors through the extension which is extracting pth roots of unity, and this is precisely what we have seen here. So pth roots of elements, and so remark. So you can consider E, EP, EP square, etc. E, P, N. So until so at some moment this will be stabilizes. So at some moment this chain stabilizes, and this E over EP to the power n is purely inseparable extension. Yeah, so let me do a break.
Yeah. How we prove it when we have character P and we consider its separable extension? How we prove that its trace not equal to 0?
Yeah. So this is not mostly non-trivial thing here in characteristic P, because you cannot just say. So you cannot do this even using the theorem on. So notice that it really shows you that it is a non-trivial fact by default. So the trace of unit is just the degree.
Yes.
But if this extension is separable, it can happen that this degree is divisible by u.
Yes.
So the problem is that, so moreover, you may have separable extension, but this coefficient can be non-zero, can be 0 in the separable extension. So the problem should be, to prove it by hands, should be rather complicated. It is not clear which transformation you should do a priori, yeah? Because at least it is not evident transformation. So as for me, I didn't think of that too much to produce the transformation, because there are much clever methods that you can prove that it is non-trivial. But anyway, the problem is that when this coefficient is 0, still the polynomial is separable, but you, in order to make this polynomial non-trivial, you have to add some powers to alpha. The change should be not only the linear change, it should be polynomial change on alpha, so that's why it is non-trivial state.
Yeah, and will we prove it?
Yeah, sure.
Okay, yes, we just.
Yeah, but now what we have observed it in one direction. Yes, so if the extension is so non-separable, then it is identical to 0. Now, so after some, so in order to prove it, so here we shall need some special formula for the trace. So, okay.
Еще раз ищем вот несепарабельное, полностью несепарабельное.
Это просто возведение в степень p, да? То есть как бы, чтобы мы сделали, это вот иллюстрация, чтобы мы сделали для элемента, да? Для элемента мы бы сделали так, что несепарабельный элемент дает несепарабельный многочлен, а это значит, что просто есть несепарабельный многочлен, его можно записать как h от x в степени p. Причем коэффициенты вот этого многочлена, они тоже все равно над f.
Ну да.
И мы видим, что корень h, это все равно, он все равно, по сути, это тот же альфа, да, отсюда, но возведенный в степень p. Поэтому просто получается, что у вас вы можете просто брать элементы, возводить его в степень p, то есть рассматривать расширение e в степени p. Просто можно после этого забыть, что мы вот этот элемент получили таким способом и искать несепарабельный элемент как e. Но только вопрос, какой именно расширение несепарабельно. Вот, как бы исходно вы брали несепарабельный элемент на d, а получали, так сказать, получали, в результате, взяв несепарабельный элемент на d, мы получаем несепарабельное расширение между e и e в степени p. Ну вот в этом тонкость. Ну а e в степени p это просто возведение в степени образ. То есть образ альфа состоит из просто p степеней, потому что p это гомоморфизм, да? Вот, то есть это уже не сепарабельное расширение, да, и этого достаточно, чтобы получить 0. Но если мы хотим максимальное несепарабельное расширение, которое здесь можно взять, максимальное чистое несепарабельное расширение, это просто максимально сколько мы в p степени можем возводить, столько надо.
А у нас что?
И оно канонически определено, заметьте. Да.
Ну, а у нас там нет примитивного элемента, может у нас какой-то еще элемент тоже не сепарабельный.
Нет, тут же тут же доказательство не используя его, а в том смысле, что мы вот этот элемент использовали, что есть промежуточное e в степени.
Не, вот это доказательство, да. Вот когда мы пытаемся найти максимальное чистое несепарабельное расширение.
То вы просто возводите в степень.
Да, а откуда мы знаем то, что мы же хотим, чтобы оно было максимально несепарабельное, значит, между e в степени.
Потому что оно чистое,
оно-то я прав. Я верю, что оно не сепарабельное. А почему из f в e в степени p в степени n?
Потому что любое чисто несепарабельное расширение, как мы там выяснили, да, это только то, что присоединено к этому степени.
Вот к нему у меня вопрос нет.
Да.
Но мы же хотим, если мы хотим найти максимальное такое, то нам нужно, чтобы...
Просто любой элемент, который не сепарабельный, то есть любой элемент, это, в смысле, почему вы не можете что сделать?
Не, почему у нас расширение f в e в степени p
все понял, что вы спрашиваете. Почему почему максимально?
Да, почему? То есть,
потому что если бы между вот этим и вот этим элементом нашелся бы еще несепарабельный элемент, то мы бы вот этим трюком нашли бы p степень. То есть вы уже применяете между этим и вот этим элементом, вы вдруг нашли в промежутке несепарабельный элемент, ну, который бы вот этому делу принадлежал. И вот этой процедурой вы бы получили, что бета степень извлекает.
Спасибо.
So, yes, I will write it that if you have alpha that is the intermediate element and the alpha is non-separable over P over F, so by previous construction we can still, so by previous construction alpha P is not, is not inside F. You can still extract P3 power of 2. So, if it is non-trivial or it is just, already so coincide. So, now I want to discuss different formulas for the trace, and suppose suppose you have separable extension now. E over F. So meaning that number of embeddings. So first of all, we shall apply. We can apply primitive element theorem. So by primitive element theorem, you can assume that E is obtained by adding one element, yeah, and also you have different, yeah. So also we have, so we have sigma 1, sigma n. Yeah, so it is degrees equal to n. Embeddings of E into algebraic closure of F. Yeah, so embeddings. And the main important reason about that if you want to calculate trace beta, so I'm writing down specifically and not to be equal to alpha, it is equal to the following, so of E over F. It is equal to simply the sum over all these embeddings, sigma I of beta, where you take all the sum of all over embeddings. So notice actually that this formula is, since sigma I are homomorphisms, then what about this formula? How we should prove? Yeah, so this was precisely, and if you want to calculate the norm, also there is similar formula for norm. It is of course the product, the sigma i's.
Yeah, the sigma i's is basis of embeddings, yeah?
Ну, в смысле, тут как бы непонятно, что значит базис. Просто у вас разные вложения. Они все, они либо одинаковые, либо разные. То есть у вас их конечное число Поэтому у вас нету, ну, как бы, то есть, ну, они же вложения, то есть, если бы, ну, как бы это были эндоморфизмы, тогда говорить, а тут, как бы, вы не можете их складывать, да?
Ну да, это правильно.
So, if, this, yes, what you say is simply that they're just different.
Mhm.
How to prove this formula? So this is precisely the formula that is based on the observation, so to which E is isomorphic. So let me put alpha f is the minimal polynomial. And alpha 1, alpha n are different roots. Of this polynomial. So you can write down E simply as follows. So you are writing down as f of x modular f. And suppose you know that, so you can notice that as we have already noticed, that trace can be calculated via basis of E where you tensor it E with any field, for example, algebraic closure. Yeah? So if you use this algebraic closure, then you will see that so you can write down calculated via I would say writing multiplication by alpha, multiplication by beta in the basis of in any basis, for example when you extend this field to this one. And let us calculate what does it mean for us. And this means that you are taking E modular f bar f. Yeah? So you are extending this field. But over this field, f is decomposable now. Yeah? So this is isomorphic. So by Chinese remainder theorem that we shall prove, so f has distinct roots. So the product of f x minus alpha I. So this is a product of algebras obtained as f bar adding x. So I shall write it like this specifically in order to see how multiplication to make. Of course, all the summands. Yeah. So this is just this is just Chinese remainder theorem. It says that if you have pairwise coprime ideals. Yeah, so actually we shall formulate it later. So maybe, I mean, for those who do not understand this equality, just put it as it is, that this algebra is isomorphic to this product of algebras. And notice that this product of algebras somehow it is a little bit stupid to write like this, yeah, because this is just saying that x is equal to alpha I, where alpha I is already an element of f tilde, so this is just f to the power n, yeah, where n is the degree. But it is reasonable to write like this, because you have if you have alpha, so because we can ask how to write multiplication of write multiplication by alpha in this basis. But alpha here is what? Is an image of x. So yeah. But by the way, and the alpha I note that alpha I just can be written as more or less as sigma of alpha. Yeah. So multiplication by alpha in this basis is just what on sum. So it is it is multiplication by x on the algebra written like this, because alpha is just alpha is in the image of x. Yeah? So alpha was obtained as an image of x, and this implies that so on factor, so multiplication by x on the factor f of x modulo x minus alpha is what? Is multiplication by what?
By alpha I.
Yeah. So this is multiplication by alpha I, just because we change x to alpha I via this relation. Yeah, x minus alpha is equal to 0. Yeah, and alpha I is sigma of alpha. And if you want to multiply by beta, so multiplication by any beta, which is some polynomial h of alpha. So h has coefficients in f. Yeah? So is equal to on the factor f x minus alpha I is what? Is multiplication by what?
By h of alpha i's.
Yeah, h of alpha i's, but better to say yes, of course, h of alpha I, but we're writing down as h of sigma alpha. We commute sigma, yeah? And we use it that it is simply sigma of beta. Yeah? So you see that this choice of basis allows us to diagonalize operator. So we diagonalize operator. Operator image of B. Multiplication by B. In MU basis. And we have obtained this, so that is multiplication by sigma beta. So the trace is just, trace of beta is just a sum of sigma I of beta. So yeah, and of course norm is the same. Yeah, so norm is the same for. So the main reason is that we have we are first of all we are allowed to change the basis of the field and the algebra is no longer separable anymore, but it is comes so the operator becomes diagonal on these factors, and this will be used also later. So it is important for us to this kind of argument will be important. Yeah. So for us for other number theoretical observation. That's why we're recording it. So yeah, now how we can prove that the trace is non-trivial? Yeah, so for this we need linear independence of the following proposition. This is by Artin. Yeah, so suppose this is a linear independence of characters, so G is an arbitrary group. So what we will use in this formula, yes, so that these sigma i's are homomorphisms, so they are in particular group homomorphisms of a multiplicative group of the field. And now we take psi I characters, so homomorphism to some multiplicative group of the field. So K is arbitrary field. Homomorphisms. So and chi I are not equal to chi j, for I is not equal to j. Yes, so they are pairwise distant. So then chi I are linearly independent. Yeah, so of course, meaning that if you take a linear combination, or yeah, so linear independent over K, yeah. So over K, yeah. So since you can write down yeah, so meaning that yeah. So let me write down the proof. Yeah, so meaning that you are not able to write down the linear combination like this. Yeah, so for some lambda I that belongs to K, and that holds for any G inside G. Yeah. So suppose not, and you have this linear combination. Yeah, so of course idea is to reduce this linear combination to the smaller one, and this is very simple. Yeah, you just change G to GH. Yeah. Yeah. So so that you are, and you have a new linear combination that looks like this. Yeah, and this is of course this is of course equal to lambda I. So the character is this is homomorphism of multiplicative groups. Yeah, so that the character is multiplicative. And you multiply this. Suppose that lambda 1 is not equal to 0. Yeah, so multiply first inequality by chi1 of each and subtract. So you shall get the sum where I will be bigger or equal to 2. And you will write lambda I, chi I of G, sigma I of H, minus chi 1 of H, equal to 0. So what you shall get by induction, yes, so notice that we should, in order to do the things work, we should use that the characters are pairwise distant. So in order to do it, it is we have to settle down the choice of H. So choose H such that ki of H is not equal to k1 of H for I such that lambda I is not equal to 0. Yeah, so in this linear combination there are at least two factors that have not zero coefficient, and for one of them will be taken to be chi1, and for the other, which is chi I, we can take H such that the values of chi are different, and this can be done because we have assumed that chi's are different, so that on one element there will be an element on which they have a distinct value, and by induction this linear combination has smaller number of terms. Yeah? So this linear combination has a smaller number of terms. This implies that it is trivial. Okay? So that is. And now, out of this expression, we can easily see that as a corollary that you have trace. Now the trace is of beta. We have written that it is sum of sigma alpha of beta. This is linear, so sigma i's can be viewed as homomorphism of E star to K. F is so this can be put as F, so this is G in our theorem, this is K. Yeah? So you have characters So just embeddings are tautologically characters. So even if they are images are distinct, the same, so what is important that they behave differently. Yeah? So on the elements of the group. And this is a particular linear combination, so trace of beta is non for some beta. In as the so you see that if the extension is separable, so that means that it is diagonalizable. And then it is non-zero. And from the viewpoint of decomposition of algebras, for example, if you think of on it in more general setting as decomposition of representation, it is more or less evident here because diagonal representation has non-trivial trace, diagonalizable presentation. And if you have non-separability, meaning that you will have nilpotent components, but so that will make your trace zero. So yeah, so let me see. Yeah. So now let us use use the trace. Yeah. So for some, so we shall do this application. So yeah, remark. Yeah, so now we are now I want to pass to the proof of the theorem of finite generatedness. Yes, so and now we are thinking about so suppose you have field extensions, so you have A, you have B here. So first of all, what can be said about trace? Yeah. So suppose B, an element is integer over F, is integer over A. Yeah. So it is a root of some polynomial. And it is a root of this polynomial. So notice that all BI's are integer. And if you are thinking about sigma, yes, so if you apply sigma to B, sigma I to B, it is of course still the root of this polynomial because sigma preserves the coefficients of the polynomial. So still root of F because it is sigma root of sigma of f of t, which is so that's why yeah. So just yeah, and it is still root of the same polynomial, so it is integer. So this implies that the trace of sigma I of b, trace of b, which is the sum of, yeah, and here we assume that it is separable extension. Here we have written sigma I of b. But this is also integer element. And in the same time, it is an element of f. So when so remark that
Why is it the element of f?
because the trace of E is an element.
Oh, yeah, of course.
Yeah. So and this means that this is an element of f. So this means that if A is normal, A is integrally closed. So when A is integrally closed in F, then this implies that trace of E over F of B lives inside E. Just because this is integer element and it is an element of F, so that the meaning that integral that A is integrally closed, meaning that this such elements are really the elements of A. So this is what is yeah. So what we do with this trace, and now we shall use this proposition. So first of all, this gives you so trace map. So the other thing that we use the trace map. So is bilinear form on symmetric bilinear form. Yeah, I shall write it down in more general settings so that because it really works in more general settings. So you can, if you have algebra L, just left shift on algebra, so you can and you define trace. Yeah, so we can define simply so having trace. Yeah, so on algebra. So given by L of A, by trace of L of A. Yeah, so we can define the bilinear form we are saying that this bilinear form is just trace of L of A, L of B. Yeah, so the which is a product of simply the product of composition. L of A. Yeah, so which is actually a trace of AB. So yeah, so this bilinear form is if but trace is a linear function. So this in general for the algebra, this bilinear form can be degenerate. It can have kernel. So for arbitrary algebra. However, you know that it is symmetric. Yeah, so because you can commute the trace of AB is equal to trace of BA. Yeah, so symmetric.
If we consider commutative algebra.
No, because the trace of
That's
it
true.
is still symmetric because it trace is
That's right.
symmetric as the map on. Because I do not commute AB, I am commuting trace, so I'm using this expression, yeah? And it is important, yeah? So also actually, this in general, for non-commutative algebra, there is an option. So you can have A, B, C. So this form is invariant from the following point of view that ABC is equal to ABC. This is associativity. Yeah, just so this is why this form is called sometimes invariant form because it is consistent with multiplication. And now, of course, this is important for non-commutative algebra to say this, but if you are working over the field, the situation is even better. So EF is a field extension. So let me put field extension. Then trace AB is non-degenerate by linear form. If and only if the trace map is non-zero. Yeah, so the meaning that the extension is separable. And here the reason is the following. So non-degeneracy, meaning this means that so for any A, so we have to find B. So such that trace of B, AB is not equal to 0, and how we can obtain it. But we know that there is always C, yeah? So there is, if this is non-zero, there exists C, that trace of C is not equal to 0. Yeah? So that means that we have to do out of C the element of the form AB. Yeah, so what we should do?
A, B, C minus 1?
Yeah, so A should be equal to...
No, B should be
B should be equal to...
So C, A minus 1.
Inverse.
Yeah.
А то вы сказали c минус a, да?
Yeah.
Ну, я понимаю, что...
Yeah, that's true.
Yeah. So, this means that this proves the claim. Yeah, actually. So, if it is zero, the form is completely non-degenerative. Not, then this can be done as follows. Yeah. So, then if you want to so let us apply this now. Yeah, so let us apply it to our construction. So, so now proposition. Yeah, so we can see the separable extension. So A is lives in F such that F is a fraction field. And A is integrally closed in F. Yeah, so if you have B inside the E, integral closure of A, then in E, then B is finitely generated A model. Yeah, so this, so first of all, so notice that if, so proof. Yeah, so what we have to, so notice that if you have basis omega 1, so omega n can be taken to be basis of E over F. Yeah, so the degree of the extension is equal to n. Yeah, so here, of course, we can take it by, if your extension is separable, we can take the powers of one element, but it won't be needed here. So notice that we can, so any basis for any, so notice that if you have B is, so any element X inside E can be made integer over A. Yeah, so is a root of polynomial an xn plus an minus 1 xn minus 1. So we noticed that we can multiply it by an minus 1. Yeah, so in order to write it like this, anx plus an minus 1 x an minus 1, etc. So an x is integer over A. Yeah, so an x is integer so this what we get out of here, yeah, so that we can take basis, multiply it by sufficiently divisible A, and so we can assume that A, by choice of A,
So we consider all a case that they lies in A.
yeah, all A, yeah, of course, yeah, so here, yeah, so you think that all AIs are elements of A, yeah, so you can put it to the formula. Yeah, so just clear up the denominators, and by the choice of A, we can assume that A omega 1, etc., A omega n are integer over A, so that they belong to B. Yeah, so that means that just by assumption, yeah, so still A, the model A omega I can be, so is sit inside the B. Yeah, so we have bounded from one side. Yeah, so in order to bound it from the other side, yeah, so just consider when we have bilinear form, we have a dual basis. Yeah, so
So why is for omega I there is polynomial such that each coefficient lies in A?
no, в смысле омега it, so omega i's are just elements of E.
Yeah.
E is algebraic over
Yes.
F.
Over F.
Yeah, so you are writing down polynomial. Then
Oh,
you
then
clear
you
up
clear the
yeah,
names, yeah.
denominators.
Yeah, of course.
So then so you have this inclusion. So you see that B is sufficiently big. I mean, there are quite many integer elements because still this is a basis. Yeah, and this is free module because it is already free over when you are looking at when you are allowing multiples of F, it is basis. Yeah. So this inclusion is just E omega I. You have inclusion inside E. Yeah. So since omega are basis, so since omega I is basis of E over F. Yeah. So then you have to produce opposite inclusion. For this, we shall need dual basis. Yeah, so let us take eta I be a dual basis to omega I. So meaning that with respect to bilinear form trace, with respect to bilinear form, trace AB. And yeah, so thinking of this as the form of so corresponding form. So I do not remember which precisely. So I mean, I do not remember precisely who should be inside B. So I mean this one or this one. So let me start and then let me correct it. Yeah. So suppose let me so suppose you have an element B inside B. Yeah? So let us write it. I mean, since F is a basis, yeah. So what we want to be able to write it down up to. So we want to put B inside the thing that is finitely generated. So let us put B to be lambda I eta I. Yeah? So just eta I is a basis. Yeah, so let me recall that dual basis is just you have. Что говорит?
Да, я просто думал, что вы имеете в виду двойственный в смысле в Е крест, ну, в Е со звездочкой, а вы имеете там
Не, ну это имеется в виду, что относительно билинейной формы, да? То есть буквально Е крест, но у вас есть омега J это символ Кронекера. Да? So let us recall that in order to omega i's are elements of yes, то есть я правильно написал, кстати. So omega i's are elements of B. Yeah? So let us recall this one. Yeah? So how to if you want to find coefficients lambda I. So what you should do? You should pair element with a dual basis. Yeah? But here pairing is the following. So just I mean in general, if you have pairing EI is a basis. So let me write down this as a separate remark. So basis, and the LJ is a dual basis. In the set of functions. Yeah, so meaning that Lj of EI is delta ij Kronecker symbol. Yeah, so then if your vector is written as lambda I e I, yeah, so in order to find coefficients, so you may think of Lj as just a coordinates. Yeah, so you are just applying Lj to V, and this is just applying Lj to the, since these are linear functional, to all Li. Then you have Kronecker delta symbol, and you have lambda I times 1. Yeah, because so in order to find lambda I, you just apply dual functional to this one. But dual functional is just this Li is in our setting. Yeah. So in our situation, so Lj of x is equal to trace of multiplying by dual basis at so here omega plays. So here we are having basis by lambda, so you are writing down like this, yeah? So Lj trace is obtained by the functional looks like multiplication by omega j and taking trace. Yeah? So we're in a sense applying bilinear form to where you pair with the dual basis. And then you are, in order to write this down, you simply write down trace of B omega j. Yeah? And this is just, this will be the sum of, yes, so lambda I trace beta I omega j. So this is precisely lambda j. So I'm just rewriting this thing for, I mean, precisely this thing for using, I mean, for nothing, for illustration that something has occurred here, but of course this is precisely, yeah, so that calculation we have done before. And now you see that, that means that you multiply this equality by omega j and take trace. Yeah? And here, if you b is integer, so b omega j belongs to b, and this implies that trace belongs to b, to a. So lambda j belongs to a, and you see that b is obtained. So you have put b inside the sum of a eta I. So we have bounded b between two modules. B was bounded between. And notice that if you wish, you can make eta I equal by multiplication. So if the thing is that you may express each eta I by omega j, and in order to do it, you should use probably denominators.
Yeah, that's true.
But clearing up denominators, you we can write down eta I as aij omega j. Yeah? So aij tilde, and d is common denominator. And so this means that b is contained in 1 over d, a omega I. So this means that b sits between two things. Yeah, so just b contains a to the power n, and b sits in 1 over d, a to the power n. Yeah, so this is finally generated model.
Yeah, can you say how we prove that the left inclusion? So
Лево, просто,
Yeah.
просто вы берете базис.
Нет, просто
Да.
в нашем доказательстве как будто
Да.
мы доказываем, что для каждого омега и существует какой-то элемент из А, умножив на который мы попадем в Б.
Да, но возьмем все вместе. Произведение этих элементов.
Ага.
Для каждого и. Если мы умножим вообще весь базис, то они все попадут в Б. Но поскольку А это элементы из F, они останутся базисом.
В смысле мы просто меняем базис.
Да.
Ну да, окей. Ага, понял.
Ну давайте я, может, это допишу здесь. Ну, то есть для каждого, yeah, so this means that for any omega I there exists ai tilde such that ai tilde omega is an element of B, yeah? So put E equal to the product. This is an element of A, and in particular an element of M. So they are integer over A, and they are still basis. Still basis over F. Since A belongs to F. Okay. То есть тут правильно. Yeah, so notice that this has interesting corollary. So when we consider, so remark, when we consider unique factorization that principal ideal domains. So meaning that any ideal is principal. Yeah. So ring A, so such that any I is a principal, meaning that I is equal to A. Yeah, so for some n. Yeah, so that we have a theorem that submodule of a free module over principal ideal domain is also free. So just any m in the free module where A is a principal ideal domain. This implies that M is free. So isomorphic to a to the power k. And actually, so it after a change of basis, so meaning that both in M and both in M and A. So meaning that just a submodule can be thought of written in terms of f1 fk. So in the basis e1 etc. en. Yeah, so you're writing down it as the matrix, and by right and left multiplication you may do this matrix diagonal, so it is diagonalizable. And it looks like it looks like the matrix d1 etc. dk with divisors, with some divisors. So there is a block of 0, the block of divisors, and these divisors are I mean even they divide each other. Yeah? So you are writing one d1 is divisible by d2, is divided by d2, d2 divided by d3, etc. Divides d3, and so this is the way how you can describe the matrix, and this will be useful for our later discussion. So let me finish that bit. Next time, yeah, so I plan to pass to dedicate domains. We shall prove the structural theorem on decomposition of the prime ideals. So that's up there, huh? Счастливо.